Welcome to the second video. So this will be the first video where I will show you steps in the software. The purpose of this video is to demonstrate how to code a network to be ready for the simulation-based assignment. As we go along, you will also learn about some other more general but certainly useful features in Visum. For the next few videos, we will use a model that is located in the south of Oregon. It represents a typical transport demand model in which currently a static assignment is used. For the purpose of this demonstration, the data are anonymous and do not necessarily represent reality. As I said, the starting point is a static assignment result over a period of 2 hours. So first I will zoom into the network. And switch off the link bars. You are directly guided to the bar, which you can switch off. So for simplicity, we will use the simulation-based assignment with the hybrid option. So that means we only prepare the part of the network where the mesoscopic simulation is applied, and in the rest of the network, the input data from the static assignment is used. So of course, if you were to run the simulation-based assignment in the full network, all the following steps must be applied in the entire network. So that is here only for making the demonstration a bit simpler, but also you get an overview of how you proceed in case of using the hybrid option. So first I switch on a territory. So that is the part of the network where we will later use the mesoscopic simulation. So that is basically the part that will be suitable for the simulation-based assignment. So we need to code this part. We can activate the objects in this part only. So we do that by using the spatial selection. Select a territory, and then only the objects in that territory are active. So we do not really care about the rest of the network. We always mention that we can use Visum as a data hub. So that means you can store additional data that might not affect the original calculation. So as we do now, we add data that are utilized elsewhere, in this case in an operational application. The data could also be used for the export to Visum, or it could be used just to display the data. So now let's start with the coding requirements for the simulation-based assignment. So we will start with links. And for links, we said there are 3 attributes particularly relevant. So that is first the permitted transport system. So that is already coded in the trouble demand model. And you could here basically check if your transport systems are correctly set. So you can do that via the attribute selection dialog. To define this filter, use the transport system set, and then we select truck and car. That are the transport system that we will later assign. So now all the links are active that are open for these two transport systems. That might not be a good thing to check if the transport systems are coded correctly. So you can here also use the complement that basically shows now all the links where no transport system is set, or at least car and trucks are not included. So you can see here a couple of links, and to make your life a bit easier, you have an option in the network that allows you to click only active objects. So now you can click here and you can additionally show the tool window quick view, where you have a couple of attributes of the selected network object. So here you see, for example, that the transport system set is empty. You can configure this view. For example, we do not care about volumes for public transport, but the attribute number of lanes are quite relevant. So we will add that to the view. You can navigate that according to what you need. So and now you can basically check if there are links that might be wrongly have an empty transport system set. So we go back to show the open links. So the next attribute that is quite relevant is the free flow speed. That is also something that you have coded in the travel demand model already. And you can see a classified display and see that in the central business district, the speeds are lower, and in particular, the interstate has a higher speed, up to 70 miles per hour, for example. An attribute that was not relevant for the travel demand model is the number of lanes. So that is something you need specifically to code correctly for the simulation-based assignment. You can also show that in the network editor graphically. So again, that is a classified display where we can see links with 1, 2, and 3 lanes, and you can check it that way. But later on, we will see also a different view, which might be also useful to have a look. So again, that is an attribute which typically is not required for travel demand models with static assignment. So I will go back to the overview with the classified link types. In Visum, you do not have only the chance to visualize the attributes in the network editor, you have also lists with all the attributes, and that is particularly useful in case you would like to check attribute values. You can open a linked list and you can arrange these windows with the network editor. You can either do that like that, or you can use this button here on the top. The lists can be configured using the attribute selection dialog. And once you have configured the list with the attributes you need, you can save so-called list layout. And I will use here a predefined list layout for the relevant attributes for the simulation-based assignment. So as we have seen before, it is a transport system set, the number of lanes, the free flow speed, and then there are here some adjustment factors and a calculated capacity attribute that I will explain later on. The lists are also synchronized with the network editor, so you get always a highlighted object if you click in the list. You can also fix the network view using this button, and then you get a highlight but without the zoom option. The next network objects I would like to explain are the transport systems. The transport systems contain quite important settings for the simulation-based assignment. Also for the transport systems, there exists a list, and I will open a list layout with the relevant predefined parameters. And in this list, you have also the option to use a local so-called column filter. So you can activate the filter, set some conditions here, and then you can apply this filter, and that are the two transport systems that we will later on assign. And here you can find the relevant parameters. These are relevant for the car-following model. So the default is a reaction time from 1.2, and then you can set the effective vehicle length. And here it might be useful to choose an appropriate length for trucks or for other vehicle types which might not be standard. And additionally, you have here a parameter that plays a role for conflicts. If the vehicle cannot make a movement at a junction for a certain time, then this default applies, and after that time, the vehicle will move into the junction. Now that I have explained you these parameters for the car-following model, I will go back to the link list. And here you can see a calculated capacity attribute, and this calculated capacity uses exactly these two parameters, reaction time and effective vehicle length. And this attribute indicates the maximum throughput if vehicles of that transport system were to travel with the maximum speed and the minimum headway. And this headway, of course, depends on the reaction time and the effective vehicle length. So the transport system parameters are defined globally, but here using these adjustment factors, you have the option to also calibrate your model locally. So for example, in certain cases, if you have, for example, uphill roads, or you have a lot of parking around that area, you can change the adjustment factor, and then you will see that the theoretical throughput has been changed. So that is an indicator which you can use to calibrate your model locally to more realistic values. So typically these values are 1, and if you change them, it is for the purpose of calibration. So that is all about transport system and links for now. Next we move to connectors. Also for connectors, there's usually not much to say. The connectors must have the permitted transport systems, which are already defined for the travel demand model, so there should be no change needed. However, I would like to make one note for coding models for SBA. Make sure that the connectors are not connected to nodes of control type that is different from unknown. The vehicles should enter the road network generally not too close to junctions, otherwise the junction operations are affected, and there could be unrealistic flows due to the fact that there is an entry point located. Also that you can check quite easily in a list. So you open a list for connectors, select the corresponding attributes, which I have done already. So you can see here the connector, the transport system set, and you can see here the control type. And here you can apply a local filter in case the control type is not unknown. And you can see here that there are 36 connectors that are connected to a two-way stop or uncontrolled node. So in your network, you should make sure that you either change the connector or change the control type of the node. For simplicity, I will here change the control type. I will apply a control type of unknown to these connectors, but again, note, change either the connector or change the control type of the node. You can disable all column filters using this button, and then you have the corresponding list of connectors again. So next I will go to turns. For turn types, the HCM compliance settings must be used. HCM stands for Highway Capacity Manual. So in case of the simulation-based assignment, the turn types are relevant for deriving the conflicts at junctions correctly. To apply the HCM compliance settings, you need two steps. First, under network settings, go to network objects and make sure that you have the HCM compliant calculation selected. That is in particular important for procedures where you use the intersection capacity analysis or the simulation-based assignment. Here you can basically define a default. And the second step would be to apply these values to turns. It is only relevant for the turn type. So here the active turns, the turn type is accordingly set. Make sure in case you have main nodes in the network like we have here, you do the same thing for main turns, like that. For turns, it is also good practice to check the U-turns, because an open U-turn could be the cause for unrealistic routing. That applies in particular if the network operates at its capacity. Also, that is something you can do easily in the list in combination with a filter. So for example, here we use a turn filter, which I have already prepared. You can also read turn filters via this dialog. So here we have a filter with two conditions. The first applies to the transport system set, and the second makes sure that the node or that the turn is not within a main node. So now we open the list of turns. We choose the relevant settings. And again, here you can then apply a local filter equal to U-turn. And as we can see here in the part of the network that we currently working on, there are no U-turns open. In case you have open U-turns, either make sure that these U-turns are realistic, otherwise remove the transport system set from the U-turns and close the U-turn. And now we come to nodes or junctions. As we have learned in the introduction video, junctions are modeled through their control types. And then gap acceptance applies in case of conflicts. The conflicts are derived from from the node geometry and from the turn types. And then gap values, namely for the critical gap and for the follow-up time gap, are set. There are default values in Visum, and they depend on the control time of the junction and on the turning movement. As you can imagine, for example, a minor stream merging into a major flow direction has a other gap value than a turning movement that must cross the major stream. We will see that in an example. So for now, I would open graphic parameters to show the control type in the network. So we might move here in the central business district, where you can see there are a lot of junctions that are coded and have different control types. You can also see the control types in the list of nodes. So here there is the control type of the nodes displayed. Another option in list is that you can group the columns. So here you can see which control types are present in the network, and you can also see how many nodes have that control type. In Visum, we have different control types, uncontrolled, two-way stop, signalized, always stop, two-way yield, and additionally roundabout, which is not present in that network. And the unknown control type is the only one where in the simulation-based assignment conflicts are neglected. So you can ungroup the column again, and now I would like to show you the junction editor. So you can double click on a node and then the junction editor will open. You can arrange that view in the same way as I was shown previously. So here we might move it next to the network editor and switch off the legend. And then you can see also here there is synchronization applied. And you see accordingly the road layout, road network layout. So you typically, when you open the junction editor, you are on the geometry view, but maybe we come later to that, and I will start maybe here with the top and open first a junction editor layout. So, and here we will, see a node. This tab might not be very relevant, but it contains, for example, the control type. And here you have a visual view of the major flow direction. The major flow direction in Visum is automatically set, so it is based on the link hierarchy, which you have defined in the link types. So that is something automatically derived, but of course you can change it. Then you need to change to major flow manually. And then you could, for example, change the major flow direction to something else. In Visum, you can always do undo if you have made changes in the network editor, in the junction editor, or in any lists. So then I would move to the turn view in the junction editor. That is quite relevant because it contains the gap values, which I mentioned previously. So in Visum, as I said, we have default gap values for the critical gap value, but also for the follow-up time gap. And these values are derived from the highway capacity manual. So you can see here, for example, a gap of 5.5 for a movement that merges from the minor stream into the major stream, and of course that has a lower gap value than, for example, a turning movement that comes from the minor stream but needs to cross a stream and then merges into the major flow direction. So once you are at the point where you calibrate junctions, first make sure that your junctions are correctly coded. But if you then need to make changes, you can, for example, calibrate these gaps. You can change them, and they have typically 3 attributes. The first enables an overwriting of the default gap. So here you can now change the gap to something else. And you can see here the difference between the default and what you have set here. And that is basically a way where you can change gap values in order to calibrate junctions or the throughput through junctions. So, and these gaps depend on the control type, as I said. So that is important that is set correctly coded. So, and now I would like to come to the geometry view. That is quite an important view because that makes it also easy to code junctions or complete junction coding based on the background map. So you can here also switch on the background, and you can also change the opacity of the network objects. So you have here a good view where you can check if your coding corresponds to the road network layout that you can see in the background. You can make changes to the background here in the graphic parameters. So use a different background service or use a colored display. I will now switch that off to make sure that you can see what I would like to demonstrate now, because now I would like to show you how to code pocket lanes in the junction editor. That is quite regularly needed in order to get junctions coded correctly. So in order to code pocket lanes, you simply select here the object lane. You will see that here the display changes. In the context menu, you can choose which side you would like to create the pocket lane. Once you have created the pocket lane, you can enter a length for the pocket lane that is required for SBA in order to get realistic junction operations. Otherwise, a default of 2 meters applies, which is certainly not realistic. Then you need to code the lane turns. So like here, the right turning movement is only from that lane, but might not be relevant from that lane. So you can also see that the signal group has been allocated automatically because it was previously already allocated to this turn. So that is already done here. Make also sure that the lane turns are coded correctly. So for example, if you were to code lane turns incorrectly like that, you would basically generate an artificial conflict of movements in that area, and that would surely lead to unrealistic flows at this junction because of the conflict. So make sure that lane turns are coded correctly. The next thing I would like to show you is a way how you can check that pocket lanes have a length. So of course you can check that here as we have done that a minute ago, but you can also check the pocket lane lengths in the list. You have here a list for lanes. Also here, I choose a predefined layout where you can see the lengths of the lanes. There are some where you cannot define the lengths, that are the through lanes, but you can define the lanes which are pocket lanes, and pocket lanes can be identified by their origin lane number. So the origin lane number is not 0, and that means you deal with the pocket lane. And also again, here you can sort this column and make sure that all the pocket lane have an appropriate length that is shorter than the link length. If the pocket lane length is the same, it is recommended to change the number of lanes, of course. Yeah, I forgot one thing to mention at the beginning. In SBA, we actually do not take the transport system of links into account, but those from lanes. However, when you set up the network, Visum ensures that there is consistency between the transport systems of links and lanes. So basically, when you set up your network, they are identical. You can, for example, here add the transport system set of links, so you can see them next to each other. And if you were to group these two columns, you will see that they correspond to each other and that there are no differences. However, it could be the case that you have some lane-based applications. So for example, you would like to take into account bus lanes, taxi lanes, or lanes for HOVs. Then it is basically also the junction editor where you would need to make that changes. So it is unrealistic for the moment, but just to explain it, you can here change the transport system set of a lane, but you can only remove transport systems from the set that is available on the corresponding link. So let's assume trucks are not allowed here. You can remove trucks. So of course that is also applied at the other end of the lane because it is a through lane. And that way you can make sure that certain lanes are only available for certain transport systems in order to prepare your network for lane-based applications. So I will do undo to change that back. And last, I would like to show you the signal timings here. You have here a view where you can see the signal groups, and also here there's some highlighting of lane turns where the signal group is applied. So you can see that. In this view, you can also change either the entire definition to a different point in time, or you can also change the duration of certain phases if you, for example, move here only. Also relevant for SBA are the signal programs. So here in that network, we have only one signal program, but you can easily imagine that if you simulate traffic over a period which is longer, then different signal programs apply. Signal programs can be defined in the Visum view, you can see here your current stage-based program, and then you can create another signal program, for example, create a sequence, and then maybe change the cycle time, create a stage-based signal program, and now you might have two different programs. And also here in the Visum view, you can then add a daily program where you can allocate signal programs to different start times. So here, let's assume one program is valid from 6 o'clock, and the second program is valid from 8 o'clock. So you select here the program. So you have defined now a daily signal program where one program applies from 6 and the second one from 8 o'clock. So that might be also relevant in case you simulate longer durations for the simulation-based assignment. So this was an overview of how networks need to be coded for the simulation-based assignment. It is fairly straightforward if you already have an operational model in which, for example, assignment with ICA is used. For other models, the efforts are slightly bigger, but there are ways to get the data more quickly set up, for example, by importing SIG files or Vistro files to get junction data or control data into Visum, or by using our model to go offering. Or you can also set up just simple phases and create initial timings using the demand flows from the static model. So there are different options of how you get these data prepared. So I hope you found this video useful. In the next video, we continue with the preparation of demand, and more specifically, we will learn how a demand profile is set up for the simulation-based assignment.